All right. After looking into octet rule, we're going to look at formal charge. Now, you may be thinking, what is that? It's actually very simple. Let's say you have a molecular structure. And let's say that this molecular structure is not neutral, but it has a charge. Like hydronium we saw the other day, ammonium, sulfate. These are known as polyatomic ion. And they have some sort of charge. Well, where's the charge? Which atom does it belong to? So that's what formal charge is all about. It allows you to calculate exactly which participant, or in this case, which atom is carrying charges. Now, sometimes you'll see this in neutral molecule as well. And this is something that we're going to see if whatever you drew, it's going to be legitimate or not. So, hey, let's take a look at this. Let's take a look at the formula of formal charge. So, formal charge is equal to valence electron. So, the atom's valence electron minus, let's call it surrounding electron. Okay, so this is the formula. Valence electron of the atom subtracted to, of course, the surrounding electron of that particular atom. So let's do the examples. Okay, let's do lots of examples so that way you know exactly what's going on and how to apply this formal charge formula. So let's do one. Let's do water. Not sure why, but I always like to start with water. Now, water is a neutral molecule. That's pretty obvious here. So you can pretty much expect that all three of these participants are going to be neutral. They carry no charge. But let's test that. All right, let's take a look at this guy. Let's take a look at this hydrogen and apply formal charge equation. So with this hydrogen right here, how many valence electron does hydrogen have? Well, it has one. Well, how many electrons is surrounding this hydrogen? Now, the way to count this is that if you're connected to via a bond, okay, this hydrogen is connected to this oxygen through this bond right here. Okay, you're gonna count this as one. I know. When we're doing octet rule, these bonds are counted as two. But for formal charge analysis, we're going to count these bonds as one. So hydrogen is surrounded by this one electron right here. Okay? So this is going to be 1 minus 1. And that equals the 0. So what that means is that this H has a charge of 0. In this case, it has no charge. Let's take a look at this H. It's pretty much the same. Valence electron for hydrogen is 1. It has one bond, so therefore it is surrounded by one electron. And it too will have a charge of nothing. Neutral. Let's take a look at the oxygen. Oxygen has a valence of 6. And how many electrons surrounding this? Well, let's count. 1, 2, 3, 4, 5, 6. All right, oxygen looks like is also neutral, which is not surprising because water is a neutral molecule. Having every participant here being neutral is normal. This is actually as normal as it gets. Let's do another one. Let's do another neutral molecule before we look into those charged ones. Let's do this one. Okay, this is carbon tetrachloride. It is also neutral in nature. So let's do formal charge analysis. Let's start by looking at this chlorine. It really doesn't matter. You can see that these chlorines are all the same. So if you do one, you pretty much did all. But let's do one. So how many electrons does chlorine have? How many valence electron does it have? Well, it has 7. Minus how many is surrounding it right now? Well, let's count. 2, 4, 6, 7. Okay. 7 minus 7, that's 0. Now, if you look at the other chlorine, they're all in that same situation. 7 minus 7. 7 minus 7. And 7 minus 7. So far, all the chlorine are pointing to neutralist. Hey, take a look at the carbon. Let's see if carbon is the same. Carbon has 4 valence electron. How many is surrounding carbon right now? Well, let's take a look. 1, 2, 3, 4. That's right. Carbon is also carrying neutralness. So, hey, no kidding that carbon tetrachloride is neutral. Everybody's neutral. This is as stable as it gets. Notice I said stability, because later on we're going to take a look at things that aren't very stable, in another sense unstable. So yeah, we'll see that. We'll see that in a bit. Let's erase this. Let's erase all of this, and let's take a look at this guy. H3O plus. Now this is a charged molecule. We saw how this was made in the other lesson, okay? And we saw how this was drawn using octet rule, right? Octet rule, O in the middle, bonded to 3 H's. Make sure everybody's surrounded by H, so therefore H has to have a lone pair. So there you go. This is my hydronium. So who is carrying that positivity? Is it these is it one of these hydrogen? Is it this oxygen? Well, I don't guess. Let's do formal charge to actually find out. Let's start with one of the hydrogen. Let's start with this hydrogen. So hydrogen has 1 valence electron. How many is surrounding it right now? Well, it has 1 bond. It's going to be 1. It's always going to be 1. Hydrogen is going to be neutral. Now, hydrogen doesn't form more than 1 bond. I mean, if you see hydrogen having more than 1 bond, that structure has problems. Hydrogen can only form 1 bond. Because of that, hydrogen always seems to be neutral. This hydrogen, same thing. This hydrogen, again, same thing. So it must be oxygen, right? Probably. But let's check anyways. Oxygen has a valence of 6. How many is surrounding this right now? Well, 1, 2, 3, 4, 5. Just as we thought, the positive 1 of hydronium came from oxygen. So that's pretty neat if you think about it. Okay, so we found exactly who's responsible for this positivity. Let's do another one. Let's do this one. This is what I think was left with the other day. Okay, PO4 with a 3 minus charge. This is phosphate. If you remember octet rule, we sum up all the valence electron. So this will be 5, 6, 6, 6, and 6. And your magic number is 29, right? 29? Nah, man, don't forget about these 3 electrons right here. You're gonna have to take those 3 into account, and your magic number is really 32. Then you're gonna select the central atom, and we selected P. Connect everybody to this central atom. Okay, well, I can do that. Make sure everybody is surrounded by 8 electrons. Okay, I can do that too. Done. Now, take a look. If you were to count every single electron from lone pair to bonding pair, yes, 32 is your count. But however, let's do formal charge. 1 minus 1. This is going to be negative 1. 1 minus 1. This is going to be negative 1. 1 minus 1. This is also going to be negative 1. And 1 minus 1. This is also negative 1. Okay, this is negative 4 already. What that means is that phosphorus is probably going to be positive 1. And let's see. Phosphorus has a valence of 5. Right now, surrounding phosphorus is 4. Right? 1, 2, 3, 4. 5 minus 4 is positive 1. So if you sum up all the charges, you will have 3. And phosphate is indeed minus 3. But there's a problem here. The problem is, can you see that in this molecular structure? Everybody is charged. All 4 oxygen is carrying a charge. This phosphorus is carrying a charge. This is actually a very, very unstable situation. Now, if you're going to Google phosphate and take a look at what Google said about the structure of phosphate, you'll notice that it doesn't look like this. Oh no. And in fact, phosphate actually don't look like this. This is a very unstable situation. There's something that you can do to make this better, the one that really exists. But however, in order to do that, you need to know one piece of information about phosphorus, is that phosphorus can hold, or be surrounded, I guess, can hold 10 valence electron. Every other atom, because of the octet rule, likes to be surrounded by 8 electrons, unless your name is hydrogen. Okay, everybody wanted 8 electrons. This phosphorus right here is surrounded by 8 electrons. Okay, but phosphorus says, hey, because of my d orbital, I can take more. I can take 10. And that's exactly what you're going to do. You're going to add 2 electrons in the form of lone pairs to phosphorus. Take a look at phosphorus right now. Phosphorus is now surrounded by 2, 4, 6, 8, 10 valence electron. Phosphorus don't mind that. In fact, phosphorus likes that. However, if you were to do octet rule right now and make that count, you'll notice that this is no longer 32. You added a lone pair, so therefore this has a count of 34. Do you remember what you have to do when you have more than what you are aiming for? That's right. You apply step 6 in the octet rule, and step 6 says, take a couple of lone pairs and make a double bond between the adjacent atom. And that's exactly what we're going to do. We're going to take this lone pair and this lone pair, and we're going to make a brand new bond between O and P. This will now have a count of 32, which is exactly what we want. The question is, did we fix the problem? What was the problem again? The problem earlier was that every atom carries a charge, and that is so unstable, man. Let's do formal charge again, and let's see if we fix that problem. Well, let me do this quickly. I can tell you right now that this, and this, we didn't fix anything. There's still going to be -1. Let's check this guy, and let's check this guy. All right. This oxygen. Oxygen has 6 valence electron. Now let's see how many electrons surrounding this. 2, 4, 5, 6. Whoa. Hey, now we're talking here. Oxygen now is carrying neutralness. We free him up. Whoa, this is great. Let's take a look at phosphorus. Phosphorus has a valence of 5. Right now it's surrounded by 1, 2, 3, 4, 5. phosphorus is also neutral, which is awesome. Because we looked like we just free up 2 atoms from charge. Now we have just those 3 oxygen carrying -1 each, which is exactly what phosphate is all about, isn't it? Phosphate has a 3 negative charge. And the 3 negative charge came from these oxygen. And if you Google phosphate, this is actually what you'll see. Now, phosphorus is not the only one with this special case. Okay, sulfur has a special case, boron has a special case, beryllium has a special case, bromine has a special case, and we're going to look at that. Okay, we're going to look at sulfate and bromine. Okay, just to make you guys a little bit more familiar with this. So, hey, let's quickly look at sulfate. Sulfate has a chemical formula of SO4, and this guy has a 2- charge. Okay, so let's do octet rule. So 6, 6, 6, and 6. That's a lot of 6. That's 30 plus 2. So my magic number is 32. I like to have S as my central atom, and I'm going to surround S by 4 oxygen, and I'm going to make sure every oxygen and sulfur is surrounded by 8. If you were to make the count here, yes, it would be 32, which is awesome, which is exactly what we want, right? However, let's do formal charge. In fact, I want you to pause this video right now and you do formal charge. Tell me what you got. All right. I'm sure you have unpaused the video. If you haven't, how would you be listening to me? So, I'm sure by doing formal charge, you had -1 here, -1 here, -1 here, -1 here, and +2 here. Is this a good situation? No, it's a horrible situation. Everybody was charged. Remember, this is very unstable. Can we fix that? Yes, we can. How? By knowing that S can hold 12 electrons. By knowing that, it will help, because what you're going to do is that you're going to insert 2 lone pairs to sulfur. Now sulfur has 2, 4, 6, 8, 10, 12. Hey, sulfur loves it like that. But sulfur doesn't want to remain like that if he's going to be sulfate. Okay? Because if you make the count here, this is no longer 32, but this is 36. No big deal. We'll just apply step 6 in octet rule. We're going to take these 2 and make a bond. So that's what we're going to do. We're going to take these 2 electrons and we're going to make a bond. Now let's recount. And the recount would have been 34. Well, we're not there yet. Can we apply step 6 again? Yes, we can, because there's still a lone pair here. So we're going to take these lone pair and we're going to make another double bond. If you count, this is now 32. The question is this better than before? All right, let's pause this video again and do formal charge. All right, I guess we're back. You did formal charge, and I'm hoping that you'll say, hey, this oxygen, this sulfur, all 3 of these are now neutral. Did we fix the problem? Oh yeah, we did. Is this better? Much better. Looks great. Looking nice, unlike before. So, this is exactly what sulfate actually looks like. Now, the question is, if you have sulfuric acid, if somebody will ask you to draw sulfuric acid, what would you do? Where would you insert those 2 hydrogen? Well, the logical way of finding these hydrogen is to attach them to where the charged oxygen are located. Because what you're actually putting in here is a couple of H+. Only oxygen would want to pick up these H+. Okay? These H will not be here. No. Okay? It would rather be here via dative bond or coordinate covalent bond. Okay? And that's where you'll get H2SO4. How do I know this is right? Do formal charge. Because if this is the molecule that you get, if this is really what sulfate is, okay, if you do formal charge on this little fella right here, you'll notice that everybody is 0. But if you take these hydrogen and you put them here and leave these -1, you'll notice that these oxygen will end up having a charge again. And that's where we want to get to. We want to look at a situation. We want to look at 2 situations. All right. Let's take a look at one more example. And let's see. Hey, let's take a look at this one. This is called the bromate anion. Okay? So, let's go. Br, 3 O's. Hey, do you know that this spells bro? So 7666. Okay? And your magic number here is 25. Really? No, you're going to have to remember to add this one more. So that will be 26. Br will be your central atom. And you're going to connect Br to 3 oxygen. And then you make sure that everybody is surrounded by 8. There. BrO3. Okay. Pause this video. Do formal charge. Okay. I'm sure you unpause. And you'll notice that this guy's -1. This is -1. This is -1. This is going to be +2. Right? Is that nice? Is that good? Does it look good? No. It looks horrible. Everybody's charged. We've mentioned that many times, man. We don't like that. Can we fix that? Yes, we can. Yes, we can. Because bromine is also special. Bromine doesn't mind holding 10 electrons. So let's give him 10 electrons to hold. There you go. But hey, as you can see, if you make the count right now, the numbers of electron in total is now 28. So you know what to do. You know what to do. You're going to take these lone pairs. Somebody asked me, does it have to be those 2? No, you can take these if you like. Let's take those then. Let's take these 2 lone pair away. Add another bond. This will be 26, which is exactly what this number is, and this is the structure. Is this a better structure? I don't know. Why don't you pause this video and do formal charge again? Okay. We're back. Did it fix the problem? Yes, it did. Yes, it did. It wasn't a big fix though, but at least this oxygen is now 0. Okay? This bromine is still charged, but it's not as charged. It's now +1. Overall, this is still -1, but that's what's supposed to be. Bromate is supposed to be -1. We fixed this. It wasn't a big fix. It wasn't like sulfate and phosphate, where, the fix was pretty dramatic, but hey, it's a fix nonetheless. So hopefully right now you guys are comfortable in terms of, doing formal charge, locating charges, making things better by knowing some of these specials. Let's continue. Okay, what I want to look at right now is what happened if you drew the wrong structure, or what happened if you are doing octet rule and you pick the wrong central atom. So let's do this one, HCN. Okay, we used octet rule last lesson, and we figured out that it looks like this. That's what it looks like. Okay, why? Because we picked carbon as our central atom, right? HCN 1, 4, 5, and your magic number is 10. We picked carbon as our central atom. We hooked up H and N. We surround everybody by 8 electrons. Then we know that it doesn't match with 10. We made a double bond. It still doesn't match with 10. We made a triple bond. Now it's all good. And that's what hydrogen cyanide is supposed to look like. But what if you pick N as your central atom? Okay, let's do that. Let's do that. Obviously, you picked the wrong central atom, but how would you know at the end? Simple. Continue with your octet rule. Okay? Make sure everybody is surrounded by 8 valence electron. Make the count. Okay? 2, 4, 6, 8, 10, 12, 14. Okay. 14 is not good because I want 10. I'm going to take these 2 electrons and